Okay, good morning, everybody. Today is Thursday, February 13th. Today will be the first of two videos for the lecture. So I'm just going to share my computer screen right now. So just to do a little bit of housekeeping before we get into the first video today. So of course we didn't have our lab this week because I wanted to push things back just to ensure that I am addressing or going over the material in the lectures before we see them in the lab. So that's why I postponed lab 4. We have the break next week, so we will not be having any labs or lectures. A little bit more housekeeping. Under the lectures, I've also included some links to some of the probability calculators I went over in the last lecture, the binomial distribution probability calculator and the Poisson distribution calculator. So the links are also in the slides that I'll upload, but there's some links under the lectures there so you can take a look at them. Also for the next video, we'll start to get into in lecture 6, normal distribution, and I've also put an Excel file that we'll be using as an example for that lecture. So that's all under in Moodle there. Also in Moodle, I've added under midterm exam, a bit of information about the midterm itself, right? It's going to be in 2 weeks. You'll have all day to complete it. I went over this in the last time. So it'd be about 40 to 50 questions, various formats. You might have to use Excel or JAST, so keep those handy. And the material is up to the end of this lecture series, the end of probability part 2. I've also posted the practice exam, so it'll be open later today at 11 o'clock. So you can see there's 46 questions, the last few of them being some calculations, Poisson, binomial, and normal distribution, which we're going to be looking at today. So the course housekeeping out of the way, let's get into, before we get into the lecture material itself, thought I'd go over kind of something interesting. Just more of an FYI, you won't be tested on it or anything, something called the Monty Hall problem, which kind of brings together statistics and psychology. So the Monty Hall problem has to do with why it's called Monty Hall. It used to be a show on TV in the 70s called Monty Hall. And a big part of the game was that the contestant would have to pick door 1, 2, or 3, and there'd be a car or something really good behind one door, and the other 2 doors would have something not as good behind them. So that's the premise of what's just called this Monty Hall problem. And the rules of the game are this. So you're given 3 doors. 2 of the doors have goats behind them, right? You do not know, of course, what's behind the doors themselves. 2 of the doors have goats behind them, and then 1 of the doors has the prize, something like a car. So you have 3 doors. So you pick 1 door, but then what happens is that the game show host, right, opens 1 of the doors that you did not pick to reveal 1 of the doors that has a goat behind it. So the kind of the crux of the game is that now knowing this, do you stay with your initial door that you picked, or do you switch to the other door? Is there a difference, or is one choice better than another? So you might want to pause the video right now and think about what you would do. You've picked 1 door, right? The host opens up another door to show you a goat. Do you stay with your initial pick, say it's door 1, or do you move to door 2, or does it matter? So just a little cartoon, right? So you pick 1 door, you're shown a goat behind the 3rd door. Do you switch, or do you stay with your original pick in terms of doors? So you can actually do the calculations here. Here's the link down the bottom here. You can set it up and you can, right, either decide to go with your original pick, right? It shows you which door has a goat behind it, and then you have to pick whether you're going to stay with your original pick of door or you're going to switch it. And then it shows you over repeated trials what your win and loss ratio is. So I actually went to this link right here and I did it about 100 times, both for staying with your initial pick. So this means that I pick one door, I'm shown where the goat is, but I still pick the same door that I initially picked. So you can see I did it for about 100 tries here, and I came out with a win percentage of about 38%. Okay, so that's again staying with your initial pick. 38% of the time I won the car. So less than 50-50, right? But what if I change my initial pick? So again, I did about 100 tries. You can see the rate of success is a lot higher, nearly 70%. So there is a big difference, right, between whether you stay with your initial door that you picked or you switch once you learn which other door has a goat behind it. And here just a plot showing you how the different probabilities work out, right? If you keep with the same door, this is the number of tries, right, along the x-axis, and this is the probability of success. So you can see that basically it evens out to about a 1 in 3 success rate. But on the other hand, if you switch your choice after you see which door has a goat behind it, you can see now that you have a success rate of getting the car of about 2/3. So why this big difference in success between staying with the original door or going with the other door? So again, the correct answer is that you do want to switch. Okay, so the idea behind why this occurs is illustrated here. So let's imagine on the left here, you first pick door 1, that's where the pointer is pointing to, that's where the car is behind. Go behind door 2 and door 3. The game show host opens door 3 to show you a goat, so that one's eliminated. So now do you stay with your original or do you switch it? In this case, if you switch from door 1 to door 2, you're going to lose. Choice 2, right? You pick door 2. The host shows you door 3 with the goat behind it, and you decide to switch this time, switching from a goat to a car. So this time you won. And then choice 3, your initial choice is door 3. You're shown a goat behind door 2. And this time, if you switch from the goat to the car, of course, you win again. So you can see 2 out of 3 times, if you switch, you win. But if you stay, you're more likely to lose. So to further illustrate this, instead of using 3 doors for this problem, imagine instead we're dealing with 100 doors. You pick your door. This is the door up here that you picked, right? And imagine this time, instead of the host just showing you one other door with the goat behind it, he shows you 98. He opens up 98 doors with goats behind them. So what are the chances that you initially picked right, 1 out of 100, or now it's down to 1 out of 2? So kind of the same idea. It's a greater rate of success to change your original pick to the other door than it is to stay with your original pick. So just something interesting, again, kind of mixing the idea of stats and probability with psychology. All right, so getting into the substance of today's lecture. So we're carrying on with our basic probability, part 2. So at the end of this lecture series, that's all you'll be responsible for in terms of things to study for the midterm in 2 weeks. And so far, last time we looked at the binomial and Poisson distributions. Now, an important thing in how they are similar to one another is that they're discrete probability distributions, in that you're trying to figure out the probability of some occurrence for a whole number, 1, 4 times, 8 times, whatever. There's no fraction, no decimal. Today, we're going to look at the normal distribution, which is not a discrete distribution, but a continuous distribution. So you can find with the normal distribution the probability of a number that is a fraction or a decimal. So a big important distinction here is that the binomial Poisson distributions are discrete, while the normal probability distribution is continuous. right? So we all kind of have an idea about what the normal distribution is, right? It's a distribution which is symmetrical, it's unimodal, right? But you can see here we have three normal distributions with three different means. The same dispersion, right? Same standard deviation, probably the same coefficient of variation, but these three normal distributions have different means. But we can also have distributions with different means and different amounts of dispersion and different units, right? So imagine we have this normal distribution here. Maybe it's the height of people in a town, right? The units here are in centimeters, and here's the frequency. Okay, so you can see this is the normal distribution for centimeters in this case, units in centimeters, but maybe our units are in kilograms. Still a normal distribution, right? But now we have kilograms for units, or maybe our measurements, our data is in temperature, degrees Celsius. Still a same normal distribution, but with a different dispersion, right? You can see the shape's a bit different, but it's still symmetrical. It's still unimodal, so it's going to be normal distribution. But you can see not only are the units different for these three normal distributions, but the amount of dispersion away from the mean is also different. So how can we transform these normal distributions with these different units into and standardize them into something common? Standard, in other words. Well, we can calculate something called a z-score, sometimes called a z-value. I mostly referred to it as a z-score, although I might use z-scores and z-values interchangeably. So we can take those distributions, those units, and transform those data values into z-scores. So how do we calculate this z-score? Well, here's the formula that we're going to be using throughout the rest of this lecture, right? So our z-score, z here, is determined by the raw data value, in this case x, subtracting from that the mean, the population mean, and then dividing that by the standard deviation. Right, so once we standardize our data, right, we can compare it against a normal distribution with our z-scores, and then what's helpful about that is that we can determine the probability of randomly selecting a certain value or a certain value between two z-scores. So we're relating the area underneath the normal distribution to the probability of the occurrence. So again, we're transforming this raw data. This is our X data here, centimeters, kilograms, degrees Celsius, and we're using this formula up here to transform those values, those X values, into unitless z-scores, right? So we've gotten rid of the units. So now we can start comparing these normal distributions without having to deal with different types of units. We could just use the z-scores to describe our normal distribution, right? So again, the idea of standardization is that we have this normal distribution with some actual units of measurements. We take those actual units of measurements using that formula, and we convert that into the standard normal distribution. So how do z-scores relate to probability? Well, we'll see is that we're going to figure out the probability of the occurrence of some event by the area that is found between two z-scores. So the main idea here is that the area underneath the curve within the normal distribution is equal to the probability or the likelihood of that score occurring. Don't worry, we're going to go through lots of examples to illustrate this. So again, the idea with the central limit theory is that when we're dealing with a normal distribution, we have a much higher probability of randomly selecting a value around the mean than it is a value far away from the mean, either it being a lot higher than the mean or a lot lower than the mean. Again, the central limit theory. So one thing to keep in mind here, so here we have a standard normal distribution with our z-scores, 0 being the mean or mu, 1 standard deviation, 2 standard deviations, or 3 standard deviations above. But remember that the area, the total area underneath this normal distribution curve, once we standardize the data, is equal to 1, right, which is equal to 100%. Right, so all the area underneath this normal distribution curve is equal to 100% probability, otherwise written as 1 when working with decimals. But often we're dealing with occurrences which are less than 1, right? So illustrating here, if we're dealing with a z-score going from -1 below the mean to +1 above the mean, the area between those two z-scores, -1 and 1, is equal to 0.682. So 68% of the area, or the probability, is located between -1 and +1, meaning that if you pick randomly a value, the probability that that value would be between -1 and +1 z-scores is going to be 68%. Right here, we have a probability of 0.841, right? Going from the left tail all the way to 1 z-score, +1 z-score. So all of the probability, the area from the left side of the curve all the way to 1 standard deviation covers 0.841 or 84.1% of the area underneath that curve. One thing to keep in mind, important, is that both sides of a normal distribution contain half of the probability. So 0.5 probability for all the area to the left of 0 z-score, and 0.5 or 50% probability for all z-scores above the mean. Right? And then we have another example here where we have a probability of a 0.159 for the probability above 1, right? So what you can see here, if we added up the probability for this normal distribution here, 0.841, to the probability for everything above a z-score of 1, those two probabilities would add up to 1, or 100%. Right, so essentially we're relating these z-scores, right? So a z-score of 0 is equal to the mean, or mu, and then a z-score of 1, 2, and 3 relate to 1 standard deviation, 2 standard deviations, and 3 standard deviations above the mean. Same idea with negative z-scores, right? Z-score of -1 is -1 standard deviation below the mean. A z-score of -3 is equal to -3 standard deviations below the mean. So these z-scores are essentially the number of standard deviations either above or below the mean. And again, right, how we're calculating or transforming our data is that we're taking our raw data values, right, maybe from a survey, and we're using this formula down here to convert those raw data values into our z-scores. So how do we determine, once we have our z-scores, how do we determine the probability of a certain event occurring, or randomly selecting a certain raw data value from our population? So to do this, I'm going to show you a couple different ways. The way that I was taught before we had a lot of online calculators was to use a probability table. So it's basically a lookup table where you relate a z-score to a probability, or as we'll see, you relate a probability to a z-score. And there's two main types of z-tables. Sometimes they're called, I'll be referring to them as z-tables. First one's a cumulative z-table, which starts from the left tail and goes all the way up to the z-value itself. And then the other one that we'll be looking at is the distance from the mean z-table, which basically just gives you the area underneath the curve going from the mean up to the z-value. So as you'll see, we can use either of these tables, either the cumulative or the distance from the mean, but sometimes there's advantages to using one or another based on what type of problem that we're dealing with. Right, so with our cumulative table, right, so our middle point right there is always going to be the mean equal to a z-score of 0. To the left of the mean, we're going to have negative z values, and then to the right of the mean, we're going to have our positive z values. And cumulative, meaning that we basically are going to be adding up all of the area underneath the curve in blue here, going from the extreme left side of the normal distribution up to the z value itself. So if we had a z value here, say it's 1.5, the probability for a cumulative z table is going to add up all the area underneath the curve from the z value all the way to the extreme left tail of the normal distribution. So here's a cumulative z table lookup, right? So how to read this table here. So the top here, you can see the cartoon of the normal distribution. Here in this case, it's given us a z, which would be a negative z value because it's less than some to the left of 0. And what it's telling us is that given this z value, it's going to give us the value of the area to the left of that z value. So how do we read our z value? By taking, here we have z, it starts out on the extreme left-hand side, minus 3.49. So the way you read this table, say if I wanted to look up the cumulative area or probability for a z value, say of minus 1.51. The way I would do it is I first go to on the left side here, I find minus 1.5, and then I go along the top and I add 1/100th onto that minus 1.5. So a z value of minus 1.51 corresponds to a cumulative area or probability of 0.0655. So you can see as we move from the extreme left tail of our normal distribution, which is right here, right? So we're going, as we go down here, we're moving to the right. So we get to 0 right here, which is equal to, right, 0.5 or 50% of the probability. And then once we keep going, we're essentially moving from the mean or 0 to the right end tail of the distribution. So you can see as we start to approach a really high z value, we start to approach 1. Because you imagine if you have a z value over here, essentially what this value is telling you is that you're adding up all of the area underneath that curve. So essentially cumulative because you're basically going from the left-hand tail, and as you move across, you're adding up all of the area underneath the curve as you move from left to right. So let's do an example here. Say I have a z value of minus 1.76. So I know it's to the left of 0. Okay, so how I'm going to look that up in this table, I'm going to go to minus 1.7. I'm going to add on to that the 6/100ths to get minus 1.76. And that gives me a corresponding area of everything to the left of it of 0.0392. Another example here, imagine this time I have a z value of 0.82, positive z value, so I know it's to the right of the mean. The way I'm going to look this up is that I'm going to go to 0.8, and I'm going to add 2/100ths onto that. That gives me a corresponding area of 0.7939. So that basically what that's telling me is that for a z value of 0.82, the area underneath the curve or probability for everything to the left of it is close to 80%, 0.7939 to be precise. So that's how you can read these cumulative z tables. So the other type of z table is the distance from the mean z table. So unlike taking the cumulative or total probability or area from the left tail, the distance from the mean takes the area underneath the curve going out from the mean or a z-score of 0. So for example, imagine I wanted to use this table to figure out the probability for a z-score of minus 1.41. So a z-score minus 1.41 is going to be to the left of 0. And I'm going to go down, and in these types of distance from the mean tables, you're not dealing with any negatives. It just assumes when you're using this type of table, you're going to take a negative value. You're just going to take the positive version of it. So in this case, minus 1.14, I'm going to take 1.1, add on 4 100ths to that. It's going to give me a probability of 0.3729. So essentially what this table is telling me is the distance from the mean out to that Z value. So same table, distance from the mean table for our previous example, 1.1, and then I wanted to add on 4 100ths onto that. That gives me a distance, right, or a probability area underneath the curve of 0.3729. So imagine instead of minus 1.14, the same thing if I have a Z value of positive 1.14. I use the table in the same way because I'm just concerned about the area underneath the curve going out from a Z score of 0. So in this case, right, same kind of idea, but now my Z score, right, is positive, but I get the same result because it's basically the same area away from the mean itself. Okay, so now that we have a little bit of idea how to use these tables, let's do some calculations. So in these calculations, I'm going to be giving you need essentially two things. You need your mean and your standard deviation. And you're going to be using that to do two primary types of calculations. The first one is that you're going to be determining a probability or the likelihood of getting a certain X value. Remember, our X value is our raw data value. So this first scenario, which we'll be going over first, is basically the probability of getting a certain X value, given that it's a normal distribution. And then the second scenario is that we're basically going to reverse that. We're going to basically be determining the X value based on the given probability. So instead of getting probability of a X value, we're going to be getting the X value for a certain probability. Okay, so again, the info that we need our mean of our data set, and we need the standard deviation. So let's do an example here. It's going to be doing a few different versions on the same kind of scenario here, looking at heights in a class. So the scenario here is that imagine we have heights of students in a class with a mean of 68 inches or 5'8", with a standard deviations of 4 inches. So the big assumption here, and we'll get into this in the next video, is that our data, in this case height, is normally distributed. Okay, so we'll be going over ways and techniques in the next video to determine whether your data set is normally distributed or not, and whether you can do these types of probability calculations once your data set has met that normal distribution assumption. But assuming that your data is normally distributed, say that you have a mean of 68 inches, a standard deviation of 4 inches, given that, what is the probability of being taller than 74 inches in this class? Okay, so in other words, what's the probability, P, that your X raw data value is greater than 74 inches? So how are we going to go about calculating that given our normal distribution? So the first thing you likely want to do is kind of visualize where the raw data score is, in this case, X equals 74 inches, within your normal distribution, right? So we know that our mean, mu, is 68 inches. We know that our standard deviation is 4 inches. So we know that for one standard deviation above the mean, adding 4 more inches is going to give us 72 inches. 2 standard deviations is going to be 76 inches. So if we know that what we're trying to figure out is for X equals 74, we know that raw data score, right? There's our standard deviations. We know that a X value of 74 inches is going to lie somewhere in between +1 standard deviation and +2 standard deviations. So we can kind of visualize where, right? If we're wanting to know the probability of randomly selecting somebody taller than 74 inches, we know that our probability is relatively low compared to if we're trying to get the probability of selecting somebody shorter than 74 inches. So just to visualize again the problem, there's the mean height of the person in the population, which is 68 inches. Right, standard deviation of 4 inches within our population. There's our person of interest, who has a height of 74 inches. And essentially what we're trying to do is figuring out the area underneath the curve above that raw data score of 74 inches. So we're trying to figure out the probability or the area underneath the normal distribution curve from above 74 inches. So how are we going to do this? Well, the first thing we're going to do is calculate the z-score. We're going to standardize our data. So there's our formula again, where our z-score is equal to our raw data score minus the mean divided by standard deviation. So in this case, right, we have a raw data score, x of 74. There's our mean, there's our standard deviation. And that works out to a z-score of 1.5 plus 1.5. So if we go back to our diagram here, right, we know that our x raw score of 74 inches is equivalent to a z-score of 1.5. So again, z-score is the same basically as standard deviation. We know that this x score of 74 inches lies basically in the middle between 1 standard deviation and 2 standard deviations above the mean. Okay, so once we got that calculated, our z-score of 1.5, let's use the cumulative table to figure out what our probability is going to be. So let's go to the cumulative table right here. So for a z-score of 1.5, right, 1.50, that gives us a probability or area, cumulative area underneath the curve of 0.9332. Right? So according to the probability cumulative table, right, there is a 0.9332 chance of randomly selecting somebody with a z-score of 1.5 or less. But that's not what the question was asking, right? We wanted to know the probability of randomly selecting somebody taller than 74 inches. But since we know that the total probability underneath the normal distribution is 1, all we have to do is basically take that probability that we looked up in the cumulative table, subtract it from 1, which gives us a probability of 0.0668, or around 6.7%, which makes sense again because, right, we can see that there's a very low amount of area underneath this extreme right part of the normal distribution above 74 inches. So essentially, the way to look at it is that the probability of selecting somebody randomly with a height less than 74 inches in this population is about 93.3%, while the complementary probability, basically selecting somebody randomly taller than 74 inches, is 6.7%. If you add 93.3 to 6.7, you get all the area underneath the curve. In other words, 100%. Okay, so let's do the same scenario, the same question, but let's now use not the cumulative Z table, but let's use the distance from the mean Z table. So here's our Z table from the mean, right? So we're going to look up, again, our Z value of 1.5. This time we get a probability of 0.4332, right? So that probability in this case corresponds to this blue shaded area, right? The area underneath the curve going away from the mean. But remember that since each half of the normal distribution has a probability of 0.5, basically all we have to do to determine the amount of area above our Z value of 1.5 is that we take the 0.5, which is the total right part of our normal distribution, subtract that 0.4332. Sorry, this should be 0.4332 there, not 0.9332. And that's going to give us a probability of 0.067, right, which is in percentage is 6.7%. So again, sorry, that's an error right there. That 9 should be a 4, right? So again, right, the way that we can read this is that the Z value of 1.5 covers an area of 0.4332 out away from the mean, or the Z value of 0. Since each of the halves of the normal distribution has an area of 0.5, right, we're going to subtract the 0.4332 in the blue away from the 0.5, which is going to give us the remaining probability or area, which works out to about 6.7%. Right, so as expected, we got the same answer using either the cumulative lookup table or the distance away from the mean lookup table. So, like I said, the way that I was taught is to use these lookup tables, but there's lots of online Z-score calculators and probability calculators they can use. Here's one, right? Here's the link right here. So if we go into it, right? Basically, you're going to enter the same data. There's your raw score or X. There's your population mean or mu. There's your standard deviation sigma. So for our case, right, our population mean is equal to 68 inches, but don't enter the units. Standard deviation of 4. And our raw score that we're interested in is 74. Hit calculate. And you can see that it spits out, calculates our Z-score of 1.5. You can see it also gives us our probabilities. Probabilities of being less than 74 and probabilities of being more than 74. So you can see here a probability of more than 74 is what we calculated using the lookup tables. We can also, a little bit lower, we can enter the Z-score itself, hit calculate, and it gives us all the probabilities, right? So again, our probability of our X value, right, being less than 1.5 is 0.933. The complementary is 0.068. So essentially, the way to visualize it now is that there's a 93.3% chance that we randomly select somebody that's going to be shorter than 74 inches. And there's a complementary 6.7% chance that we're going to randomly select somebody from this population that is taller than 74 inches. Okay, so let's do another example, because that's the way to learn how to do these kinds of problems. So staying with the same premise, right? Again, a mean of 68 inches, standard deviation of 4 inches. Now we're asking, what is the probability of being shorter, or finding somebody, picking somebody randomly that is shorter than 66 inches? So let's first visualize where 66 inches, that raw data score of X, is going to be on our distribution. So since 66 is less than the mean, right, it's going to lie somewhere between the mean and 1 standard deviation, or minus 1 Z-score below the mean. So what do we have to do? Well, first of all, we have to calculate the standardized Z-score, again, using this formula here. So if we plug in our data this time, we're dealing with an X score of 66, the same mean and same standard deviation. We do our arithmetic, we get minus 2 over 4, which is going to give us a Z-score of minus 0.5, which of course we know now is going to be on the left side of our normal distribution. So now that we have our Z-score, let's find the corresponding probability value in our table. So for a Z-score of minus 0.5, that corresponds to a p-value of 0.3085, about 30.85%. So essentially, reading that cumulative table, because again, the cumulative table gives us the probability of everything less than the X value that we're looking for, we've already answered the question, right? since we're looking for somebody, the probability of selecting somebody shorter than 5.6 or a z-score of 0.5, based on the cumulative table, that gives us a probability of about 31%. So that's one way that the cumulative table can be handy to use if you're looking for the probability of picking something less than the probability of picking a value less than a certain level. So the way to visualize it, right? Now our person, right, for a height of 66 inches, the probability of randomly selecting somebody shorter than 66 inches is 31%, while the probability, right, of selecting somebody randomly taller than 66 inches is going to be 69%. Again, both of those are going to add up to a total of 100%. Okay, so let's now, still with the same example, let's use the distance from the mean table. So again, with the distance from the mean table, we don't deal with negative values, even though we have a negative z-score, right? We're going to flip that to a positive value. So now we get a probability value of 0.1915, which is essentially this red area right there, right? So again, in this case, the area or the probability using this type of table is the area out from the mean. So now, because we know that each half of this distribution has 0.5 in it, all we have to do is to figure out the area in blue is subtract the 0.1915 in the red away from the 0.5, which gives us the area or the probability in blue, which again is the exact same answer that we got with the cumulative table, about 31%. Right, so using both types of tables, we get the same answer, that there's about a 31% chance of randomly selecting somebody from this population that has a height of shorter than 66 inches. Okay, so far what we've been doing is taking a raw data value x, converting it into a z-score, and then from that determining a probability. Now we're going to reverse things. Now in this scenario 2, we're going to be given a probability, converting that probability into a z-score, and then finding out which x raw data score corresponds to that given probability. So again, let's go back to our same example here. So average height, 68 inches, standard deviation of 4. But this time the question is posed much differently. The question this time is, what is the shortest height among the tallest 10% of students in the class? So the way to visualize this, right? Imagine this is our normal distribution of heights going from extremely short, mean height there. What we're looking for, if we set our probability of 0.9, right? This is above 0.9, right? That's the 10% of the tallest 10% of people in that class or in that population. We're looking for the shortest value within that top 10%. So now we're looking for the raw data score, the height, the x in this case, based on the probability. So kind of the same process here, right? But now we're working in reverse. First thing is that we're going to determine the probability value. Then we're going to calculate the z value. And then from that, we're going to determine the raw data x value, height in this case, that's associated with it. So because in this case, we're looking for, we're splitting basically our population into the top 10% and the lower 90%, right? Here's our area below a probability of 0.9. And there's our area above a probability of 0.9, which is equal to 10% or 0.1 of the total area underneath that curve. So basically the way that we're going to take the probability and find the z-score is that we're going to use the cumulative table in reverse. So this time we're looking for a probability of 0.9. The closest value, remember all these black values in the middle here are probabilities or areas. The closest value in terms of probability or area is 0.8997, which corresponds to a Z value of 1.2 plus 0.08, right, which gives us a Z value of 1.28, which corresponds to a probability of 0.9. So again, we can also do this in the online calculator. Now I'm going to enter my probability of 0.9. Then I go to the calculate. You can see up here, it returns the Z value, which I just looked up in the table, of 1.28. There's our mean, there's our standard deviation, right? We do a little bit of algebra, right? We multiply 1.28 by 4, and then we so basically the minimum height for the top 10 tallest people in this population is 73.12 inches. So if we just round it down to 73, right? So basically the 73 is dividing the lower 90% of the population to the upper 10% of the population. So basically we found that the shortest person in the tallest 10% of in this population has a height equal to 73 inches. Okay. Do another example here, same premise in terms of mean and standard deviation. This time we're going to figure out what is the height that will be exceeded by 80% of the students in this population. So what is the height in which 80% of the students will be taller than? So we're going to follow the same basic steps, determine the probability value, calculate the standard score, or aka the Z-score using the table, and then calculate the final height at which 80% of the students will be taller than. Right, so step one, the height exceeded by 80% of students. So basically we're looking for a p-value, a probability of 0.2, right? Because 80% of the students need to be taller than the student, right? So we're looking for the p-value of 0.2. So to visualize this one, right? We're looking for the height. What is the x value, the height of the person at which 80% of the other students will be taller than that? So in this case, basically we're dividing 80% taller students from 20% of shorter students. So let's find the Z-score from the lookup tables. This time, we're looking for a probability of 0.2. The closest value in the table here is 0.2005, which corresponds to a Z value of minus 8.4, right? So that's going to be our Z value, and then we're going to be determining the, right, there's our Z value, and then from that, we're going to calculate the raw score, or X height value, using that same formula again. We're going to plug in our Z value, mean, standard deviation. Again, we do our algebra here, switching things around, multiply by 4, add 68 to both sides. That gives us a, wait for it, a X value of 64.64 inches. So essentially, we figured out that 80% of the students in this class or population, 80% of them are going to be taller than 64.64 inches. So if we're going to visualize this again, right, that's where our X value is going to be, which is going to separate 80% of people that are taller from 20% of people that are going to be shorter. Okay, let's do one final example which is going to be a little different in that we're going to figure out the probability getting between two z-scores. Okay, so now we're looking at the probability between two separate z-scores. So imagine our scenario is this. Imagine there's a survey done, and the results of the survey show the width of adult moose antlers follows a normal distribution, again, an important assumption we need to satisfy in order to do these calculations. In this case, the mean is 1.45 meters wide, and it has a standard deviation of 0.35 meters. Right? So that is our population. Okay, so we've gone out and measured the width of the antlers on a large population of moose. So here's a question. Given that information, what is the probability that you would randomly encounter or select a moose with an antler whose width is somewhere between 1.35 and 1.60? So again, we have our basic information. We have our mean width of 1.45. We have a standard deviation of that width of 0.35 meters. So essentially what we're trying to figure out is what the probability is of randomly selecting a moose that has an antler with somewhere between 1.35 meters and 1.60 meters. So we're going to basically follow the same essential steps, but we're going to do it for both of these values, both for the 1.35 and for the 1.60. So let's first determine the z-score for the 1.35, the lower end of our range, using that same formula. So in this case, we plug in our x value, 1.35, subtract that from that our mean, divide by our standard deviation. That gives us a z-score for 1.35 meters of minus 0.29. So in this type of question, sometimes it's advantageous to use the z-table from the mean. So in this case, right, we have a z-score of minus 0.29, which corresponds to an area of 0.1141. So that's our area away from the mean. Okay, so now let's calculate the z-score and the probability or the area underneath the curve for the upper end, 1.6 meters. Same kind of process. Now we're just going to enter in 1.6 meters. That gives us a z-score of plus 0.43, which makes sense because, right, this value is slightly higher than our average value. So now we can go back to our z-table from the mean. And this time, right, our z value is plus 0.43. We're going to look up 0.4, add 3 100ths onto that to get 0.43. That gives us an area underneath the curve of 0.1664. So that's what I'm showing in blue there. So basically what I figured out is that the area on this side of the mean is equal to 0.1141. And the area underneath the curve to the right of the mean is equal to 0.1664. So essentially to get the total probability, right, between 1.35 and 1.60, all I have to do is add up those separate probabilities. So I'll take those separate probabilities, and that gives me a total probability of 0.281, or basically 21.8%. So the way to visualize this, right, I'm taking the individual probabilities on the left side and the right side of the curve, add those together, and that gives me my total probability. I can also use the online calculator for this, because if you scroll down, you can see that it has a table here where you can enter the left or the lower z value, in this case, minus 0.29. The right bound or the high z value, which you figure out to be 0.43. I can hit calculate, and it gives me my probability between those two z values, which, as we just calculated, is 0.28. All right, so just some things to keep in mind, right? So we've looked at 3 distributions. In the last video, we looked at binomial Poisson distributions. This is the normal standard normal distribution where we're taking our raw data scores, we're transforming them into z-scores and figuring out probability based on that. Of course, a big assumption, as I mentioned before, is that the assumption is that our data follows a normal distribution. And what we're going to be looking at in the following video is some of the checks that we can do to figure out whether our data that we've collected follows a normal distribution or not. And if it does, we can do probability calculations like we just did. Okay, so that's what we'll be talking about in the next video.